The Indian Association of Structural Engineers, also known as IS-Struct-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IS-Struct-E is registered under the Societies Registration Act 21 of 1860. IS-Struct-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural engineering fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IS-Struct-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, late Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Manoj Mittal, Professor R. Pradeep Kumar, and Shri Alok Bhaumik as its president. IS-Struct-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IS-Struct-E has collaboration with various international professional like-minded associations and institutions like IS-Struct-E, UK and FIB for strengthening global connections and professional exchange. IS-Struct-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IS-Struct-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IS-Struct-E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IS-Struct-E's activities are widely appreciated and known for quality technical contents. IS-Struct-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, monthly newsletter, and Crossfall, a unique quarterly newsletter that confidentially reports structural failures and the lessons learned from them. IS-Struct-E's publications are becoming popular with time. IS-Struct-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IS-Struct-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. Reaffirming its commitment to professional excellence, IS-Struct-E launched the accreditation program in 2023. This flagship initiative empowers practicing engineers to evaluate their competencies, identify growth opportunities, and strengthen the foundation for sustained professional success. IS-Struct-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. Joining IS-Struct-E offers exclusive resources, mentorship, and networking with industry leaders. Members enjoy discounted registration for workshops, seminars, and events, along with discounted membership of FIB, opportunities for certification, career guidance, leadership roles, and enhanced professional recognition. IE Struct E has its student chapters in several leading engineering institutions as well. Membership of IE Struct E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IA Struct E is available on its website www.iastructe.co.in.
Shall I start?
Yes, sir. Yes, sir.
Friends, welcome to the webinar. Today we have got a well-renowned experienced structural engineer. The topic will be discussed by him is on structural engineering in tall buildings. The speaker's name is Engineer Abhijeet Kulkarni. Engineer Abhijeet Kulkarni is a chartered chartered structural engineer with the Engineering Council, United Kingdom, and has over 30 years of experience in civil and structural engineering, and is a reputed European consulting firm in the UAE. His profile spans long-span structures, high-rise towers, special structures, structural forensics, and industrial building structures. He has successfully led multidisciplinary teams on major projects across the UAE, KSA, Qatar, and Oman, ensuring effective cross-discipline coordination and timely stakeholder engagements. In June 2019, he returned to India as country director in structures with the British consulting firm, leading designs and peer reviews, business development, client relationship, and monitoring teams. He is a fellow of Indian Association of Structural Engineers and ISIC UK.
I think we lost.
And
Yes, sir.
member of Engineers Australia. Brief about the webinar topic. Tall buildings have always been a fascinating and statement of development. The boom began in multi-story in the 20th century and in the United States. And by the end of 20th century, it moved to Middle East, Hong Kong, and the rest of the world. India has also seen significant rise in the tall building footprints in the recent past. Buildings of height of over 2,000 meters have been on rise in many metros, including Mumbai and Hyderabad. Now, I would request Abhijeet to share his knowledge on the subject. Please, Abhijeet, please proceed.
Okay, thank you very much for this warm introduction. Is my voice audible to everybody? I could see some of the comments here saying that no sound.
Yeah, sir. What? Audible, sir.
Some of the people are saying no sound, like Ishad Khan is saying here. Then there is a few other guys saying at the top, Hari, few more guys.
I think their system have some
I
problems.
I I hope so.
Yes,
Yeah, yeah. So
please continue.
yeah. So thank you very much for giving me this opportunity. Some of you would have also participant of previous conversations on similar topic at different forums. So excuse me and apologies if I'm repeating some of the slides because it's a topic which is you have to cover in holistically. Now, other thing is because it's pretty vast topic. Structure engineering in tall building themselves are pretty vast, and then structure engineering in tall building is next level. So I would you know try to cover more sort of introduction about tall buildings, about what we should do on structures. Some topics I'll just touch upon. Some topics will be you will see the webinars in the past from IAStructE where these topics were covered. So it's a cluster of these previous discussions and some recent findings. So with that, I'm starting now. Uh, I hope my screen is visible to everybody.
Yes, sir. Yes.
Okay, perfect. So what I will cover today is why tall, obviously the general trend. Um, Council of Tall Building and Urban Habitat, CTBUH, has now renamed itself to CVU, Council of Vertical Urbanism, starting this year. So I'll give you some of the stats of that. Then we'll talk about a little bit on definition of tall building, then structure engineering considerations, some special topics. I was thinking that I will add construction, but I don't think I had time to do that. So perhaps I haven't added much on the construction. And then I'll have some reference projects. So why tall? Obviously, there are multiple reasons here, some technical, some non-technical. Technical reasons like city like Mumbai, city like say Hong Kong, New York, scarcity of land, and that is one of the reason why people want to go tall. Whereas if you see city like Dubai, you see a lot of tall buildings there, but then it's not scarcity of land there. It's more of a development close to waterfront because that's where they can put in a lot of services and they can attract a lot of investors into that. So that's why Dubai is seeing a lot of waterfront tall buildings development. And then some other areas, it's more to do with tourist attraction, job creation. Obviously, Middle East, you have seen a lot of, since 2001, huge inflow of architects and engineers and contractors in tall buildings. And then at the end of it, it's a human ego. Right? We can build, we can do, and it's not just particular country specific. It's just that human mindset that yes, today we are achieved Burj Khalifa, tomorrow we'll achieve, that Kingdom Tower in Doha, not so the Jeddah, and maybe day after tomorrow something else. So it's development of technology and how human race looks into it. Council of Tall Building, as I said, has been changed to CVU, Council on Vertical Urbanism. You can see on their website a lot of good books there. What this council does is also it maintains the record of tall buildings at various countries. You can become a member of that and you can be part of getting that database. These some of the snapshots I took it because we are obviously we are members of this company, this council. So 2024, 134 tall buildings were completed. And when I say tall buildings, they are 100-meter plus easily. And if you see the database on the right, you see that how the growth is in terms of number of buildings. And this vast amount of buildings which are in that range of 200 meter to 300 meter, right? Not many buildings are gone beyond 300 meter, very few. Multiple reasons for that. Obviously, managing those buildings and constructing those buildings becomes a challenge. 200 to 300 appears to be a sweet spot for all the developers. Now, in terms of geographical spread, and this is what Dr. Dhawan was mentioning, the tall buildings in the past have been always US specific thing, and then from 2000 onwards, it has slowly started going out of US and going into Asia. And today, if you really look at it, Asia is currently having, substantial amount of tall buildings in terms of number, in terms of under construction. And Asia, when I say Asia, it's China, India, and Middle East. And in terms of usage, more or more developers are opting for mixed use buildings rather than individual usage. And that puts a lot of pressure on typology of the structure, structural framing. Imagine a office building with a open span loaded on top with an hotel, which has rooms of certain size. So obviously that is, and then services transfer, structural transfer. So the usage of the building does demand or does impact the structural definition. In terms of all this data is available on sorry, not iStruct, CTBUH or CDU now. So the material that has been used in tall buildings has traditionally been steel, especially in the US. But slowly and steadily, if you see there towards the right, it is composite building are kind of putting, gaining popularity. And when I say composite, it is concrete encased steel columns or concrete filled tubes or composite decks. And we are currently, I'll show you some of the pictures of one of our projects, currently looking at a 220-meter 4 towers with the die-grid structures. CVU also, there's a definition in Indian code which says that 16700 tall building says that 50 meter and above, and the code says 50 meter to 250 meter is where the limit of that code is as far as definition of tall building is concerned. But if you really look at it, tall building it's a relative thing. It is, it can be a 14-story building, as I said in the middle there, a 14-story building in a kind of village or low-rise 14, 15-story building, a low-rise landscape can be tall. Whereas same building sitting in city like Mumbai, it's bread and butter, it's kind of routine thing. 14, 15-story building, even 100-meter building in Mumbai is, it's kind of a day-to-day job. So that's one aspect of tall building. Then other aspect of tall building is how you define from structural perspective. What is a definition? All these are relative terms. So the definition in structural engineering terms is basically when the horizontal loads, which is the wind and seismic and the lean effect, the P delta we call it, they start affecting the structural design. That's when the building becomes tall. Now it can be a very slender 50-meter building. It can be a 300-meter tall building. It can be anything. It is just that the impact of these horizontal forces dictating the design of the structural design, that's when it becomes a tall building for structural engineering. And then there are a few other things like technologies, number of floors. They say medium tall, super tall, and all that. But these are more of a generic specification. But structural engineering perspective, if the horizontal load starts impacting your structural design, governing your structural design, then it is a tall building. And with that comes a premium of height. When I say premium of height, it is material consumption and impact of the wind and seismic load on the foundations and the vertical load carrying elements, core walls, columns, and whatnot you have. The taller you go, the more will be the impact of these lighter loads. And then if you look at wind load itself, 0.6 or 0.61, 613 V square, right? V is again dependent on height. So V square is dependent on square of height. That's your pressure. Now you apply that pressure and get the bending moment. That's pressure times height again. So it's H cube. So effectively, wind governs or wind load are proportional to the cube of height. Right. So taller the building, more with the cube of that height. So that means the wind load will be more impacted. Similarly, you can find out on the seismic load. Excuse me. So the premium of height is one of the things that is critical, and that's something which all the structure engineers should be aware of, that I cannot, or as a structure engineer, I cannot just say that a three-story building of certain height, certain configuration, I'm just stacking that three-story building 3 times and it becomes 9-story building, or maybe 10 times it becomes 30-story building. That's not the case, right? You have to have that extra vertical load, you have to have that extra horizontal load, and then premium of that height. And if you see there on the right, second graph on the right, Faisal Khan, who's one of the pioneers of tall buildings, he has given some idea about how much would be rough order of magnitude consumption of material. In foot-pound units, I just tried to convert that into a kg per square meter of the reinforcement. Now, this is something which we all, as a structural engineers, should be aware of. Uh, One of the things I get answer questions when I start meeting clients, that what is your material consumption? Now that's a tricky question to answer, because client is looking for most efficient structural system, and client is looking for the least amount of material consumption. But at the same time, you as a structural engineer, we have to look at all these aspects of tall buildings in terms of constructability, seismic load. I'll touch upon the new seismic code a little bit in the slides. Wind speeds and wind loads, foundation conditions. So it's very difficult question to answer in the first meeting without even seeing the shape and size and architectural vision of the tall building. So I tend to tell my clients that look, all said and done, if it is building of this configuration, this typology, it will be roughly this much. If the building becomes that typology and that configuration, the material consumption, so I'll give a range rather than just saying them it will fit within this sort of a material. And structural engineering, it's striking a balance between what we are expected to have from structural perspective, like loads, material, code requirements, fireproofing, and all that on one side of it. And the second side of it is developer's vision, developer's requirement, architect's vision, construction constraints. Sometimes you might design it with certain material, but that material may not necessarily be available. May not have the quality contractor available for building that type of building. The entire supply chain, not just structural engineering in terms of grade of concrete, in terms of material, reinforcement, structural steel, waterproofing. Not just that, it also the supply chain of other disciplines. Speed at which client wants it to be built. The faster the better. That's how developer wants. But then how faster it can be, depending on the configuration. Do you have a transfer? You don't have transfer. There's so many of those things, right? And then one of the things that kills the construction, and I've seen that quite a lot in last 30 odd years, is changes, and that too late changes. You are in a construction and you start changing things. Obviously, it's a market changes. It's a dynamic thing, right? Depending on what is market requirement, client has their own vision, on ROI calculation. So that becomes a killer in terms of how you adopt your structure to meet the client's requirement. Loads, we all know there are tall buildings, there are vertical loads and lateral loads. Lighter the better, that's what I keep saying. And then the company I work for, Buro Happold, Sir Ted Happold was the founder of the company. His words are touch the earth lightly, which means keep it as light as possible. Now, when I say keep it as light as possible, obviously for every element of work, we have to challenge ourselves. Is that what we want? Do we want really have this concrete, or is this load correct? It starts from all there. And then assessing the loads correctly, like wind and seismic and temperature loads and whatnot. Yeah. Gravity we talked about. Typically we do office building, we say 4 kPa, or sometimes we say 3+1 or 4+1, one for partition, demountable partition. Sometimes it's 4+1 or sometimes 3+1. But then here is iStruct did some studies, and this is a paper in iStruct, the Structural Engineering magazine, I think about 10 years ago. And you can see that 3.1 kPa is 29 people in 6.75 square meter. Is that the load the entire building going to see at the same time? We do light load reduction. We do, proportional reduction on the height. But then the base load itself, is that what we want? Is that 4 kPa or is that 3 kPa? Is that 3 kPa or is that 2.5 plus 1 kPa? Instead of 3 plus 1, maybe 2.5 plus 1. So these are the things that obviously there's going to be, code provisions, there's going to be client demand, there's going to be future proofing of the project in terms of load carrying capacity. Maybe client want to change the usage of building down the line. Maybe the typology might change. So it again depends on how the development is going to take place. Is it the development which the client is going to manage over a period of time, next 20, 30 years? Or is it the development where client want to sell it off like residential buildings and then, move on with another project? So these things do affect. And then my suggestion to all my fellow engineers is ask these questions to client, ask them to review these numbers one more time and show them some of the advantages. Now, this is basically gravity and light load. And gravity load, as I said, lighter the better the material. Sometimes you can use lightweight concrete. Sometimes you can do lightweight blockwork, partition wall rather than solid blockwork. These days, MI1 is pretty commonly used, but the MI1, whether we are putting in concrete where it is perhaps not required. So that's another question that we should ask ourselves: that is it the efficient system for a given project? So, I mean, different projects have different typologies and different requirements. But as a structural engineer, we should start from maybe 10 requirements, and then we say that it's not possible, not possible, and not possible. And we probably settle with 4 or 5 requirements which we can adopt into design. Most of you would know wind loads and wind speed and Indian wind code. So I'm not going to repeat that. But most importantly, as I said, wind is a dynamic phenomena. For tall buildings, it affects more cube of height, and that's why it is absolutely critical that we should carry out some sort of a desktop study, if not the wind tunnel test, for some critical building. And normally I would go for any building which is about 150 meter or plus. I would definitely go for a wind tunnel test. And there are some good wind engineers around us available who can give us great guidance on how can we optimize wind speeds and how can we optimize wind loads, not wind speed. Wind speed is a bit what I can say, a bit challenging question, but wind loads, I think they can easily help us in optimizing it. It is a dynamic factor. It has its base and it has then moving factor, and then based on that you can find out the base water turning moments and distribution of wind loads. Typically, it's conducted in a wind tunnel test. This is a facility I visited about a year ago in RWDS Trivandrum location. I think they have one more tunnel there. Then we have something similar with CPP. All these, wind tech is another one. So they carry out these wind tunnel tests, and then there are codes available for carrying out wind tunnel test, methodology of that, and then interpretation of wind tunnel test. Right, 150 meters is what I would rather suggest to go for wind tunnel. Anything less than 150, if it's not slow, slender. I mean, sometimes you will have some slender buildings where even if they are 120 meters, still wind tunnel is required. But normally for a building of say maybe 30 meter by 30 meter, 150 in plan, 150 meters seems to be a reasonable thing. But then suppose you have a cluster of towers, sitting it's a group of towers being built together, then obviously the codes will not allow you to have that crosswind effects, interface interaction effect between the two towers. So in those cases, wind tunnel is the best solution. Some of the tests that we did, this was another project that I did in Middle East, Buro Tower. So we did multiple wind tunnel with a tower. The model there in blue is the specimen model for the project. The yellow that you see there on the right was the building was supposed to have constructed, it never happened. So we did multiple optioning. If the building happens, if the building doesn't happen, what happens to the next building if it's a taller? What is the impact of that on our building? Those sort of things can be done easily in wind tunnel test. And then what is critical from tall buildings perspective is we carry out all these tests, we design it, but then the lateral overall drift of the building has to be limited so that the building doesn't go into that P delta mode, significantly increase forces in P delta, and then you end up uh, pushing a lot of concrete and pushing a lot of reinforcement, maybe vertical post tensioning if the building doesn't stabilize itself. IS 16700 limits the wind drift to height over 500 for unfactored wind speed of 20 years return period. Some international standard ASC 7 allows you to take it to up to H over 400. I think ASC 7 Annex C, I guess, that gives us significantly more detailed data about wind drifts. So this is something that as a structural engineer, one should be careful about, that how much is building moving. And when I say building moving, not just wind load, the wind load will happen together with the vertical load, because that's going to be there. Now, suppose building is leaning under its own weight, that lean plus the drift of the wind, those two added together is what we should be limiting ourselves to for that HO 400 or HO 500, HO 600. Then comes there's another methodology of rake calculation for wind, perhaps not required for medium rise building, but tall flexible buildings it is required, and something called as wind deformation damage index, DDI. And this is where significantly tall buildings, especially you have internal walls like resi buildings, where you need to do this calculation at the four corners of a vertical diaphragm or vertical what you call partition walls, and find out the deformation index. And then there is a provision provided by this ATC design guide number 3. Along with the loads on wind, obviously tall building also are susceptible for wind-induced vibration, like building moving under wind. Movement of building is not that critical unless you have something in front of you that you can measure that you are moving. If there's nothing in front of you and you won't feel that movement, then it doesn't matter, because then building is safe. But if you feel that movement, which is the acceleration, then you have a problem. It's a mindset. Some people will feel it, some people will not. So codes have been developed. ISO code, there is IS 16700 has reached out, putting some numbers there, but based out ISO. Normally for accelerations for 10-year wind return period wind speed, residential buildings are limited to 15 millig. Mercantile, which is office buildings, are limited to 20 to 25 millig, and then torsional velocity is limited to 1003 radians per second. Now, why this is required? Because this is more of a human perception. If you are in a residential building, if you're in hotel relaxing, or if you're in a hospital, you are a patient. So you are already hooked with so many equipment along with you. So it's very difficult for you to mobilize quick. You are perhaps bedridden. Residential building, hotel building, you are relaxing yourself. So you're not that agile. That's why you want to have this assessment or this wind-induced jerk feeling to be low. That's why this is 15 millig, sometimes 12 millig for hospital buildings, 12 or 10 millig. In fact, sometimes they go to 10 millig as well. Whereas in office buildings, you are agile, you are standing, you are working. If you feel that building is moving, you're feeling a jerk, you can easily stand up. You can, if you feel that there's something wrong, you can, basically you're agile. And as a result of that, the codes ISO 9000, not 9000, sorry. ISO, I think 167 something, I forgot the number there. But then IS 16700 has got that data from that ISO. It kind of allows you to increase that perception of wind in terms of acceleration. Seismic load, we all have seen this. Codes have changing over a period of time. And then the recent code has, there's a lot of debate happening on what's happening with the recent new code, 16700, no, sorry, 1893 2025. Things have changed. A couple of cities have jacked up by 2. If you see Jaipur, classic example here, uh, it was zone 2, now zone 4. Kolkata zone 3 becomes zone 4. And then it has its own challenges in terms of the uh, even if the zone is not changed, the seismic force has gone up. Uh, Various reasons. Obviously, the more refined data we have, the more refined codes we'll have. I think the code might have gone through the revision because of the data that we received over a period of time, 2016 to 2026, 2025. It has, the code writers would have seen. Obviously, there's a reason behind all this, and then there's a lot of discussion, a lot of presentations are happening around India, IIT, and other RECs. I don't want to touch that because that's happening anyway. So there's a simple thing on the return period and why the code has changed. So previously, until 2016, the code never had probability of exceedance, whereas most of the international code had this probability of exceedance. And when I say probability of exceedance, it's basically how much percentage of that particular earthquake is likely to happen in a given period of time. And when I say given period of time, normally for structural design, it is a 50 years of time, right? That's how we design it. So probability of exceedance of that particular level of earthquake in that 50 year is what is called as, that it gives you that return period calculation. So I've done some quick checks here, and this is pretty simple. You can look at Google and you can find it. So 2% of probability of exceedance in 50 years means the earthquake that is supposed to hit or to achieve that 2% of probability in that 50 years will have a once in 2,475 years sort of return period. Similarly, 10% probability of exceedance in 50 years is 475. So normally this 475 is being considered as ultimate level earthquake, and then anything beyond that then goes to MC level. The code has defined normal building, important building, critical building, and special buildings. And based on that, each typology of the building and who defines it, that is a question. Mostly, it will be defined by occupants, and then the client, and then depending on the usage of the building. But I think it's a matter of discussion that whether a particular building should be normal building or important building. We used to have importance factor, if you remember, in previous code, that is now become 1, and whereas this criteria of four typology of the building are being picked up. And for each of those typology of the building, the zone factor is defined for limit state method and working stress method. Why working stress method is given? Because that's what is going to be used for your calculation for foundations, your calculation for seismic drifts and whatnot you have, right? Uh, so there, you can see this code and you see, I'm zipping past because I have so many slides. But the criteria here is, or the idea here is, define the building, category, find out what is the design earthquake, and then work on that. Now, why the code has not gone with load factor? Because the earthquake that you are going to get, it itself will have a load factor built into it. So we did a quick check on how much it will take for zone 2 to zone 6 for a normal, important, critical, and special building, just by getting the ultimate level, limit state level earthquake divided by working state level earthquake. And you see there on the right bottom, the built-in load factors. So there's no point debating on earthquake has increased. Actually, we should be comparing the earthquake that we are getting from 2026 version to 2016 version, or 2025 version, 2016 version, by multiplying the factor of 1.5. So that's why load has not significantly gone up. Maybe a little bit more on this critical building here. Important building, maybe zone 2, zone 3, little bit gone up. But generally, if you see here, it is still hovering around that 1.5 factor. The only thing in the code says that you have to now, you in the sense, the structural engineer, along with the consultation with the client, has to define what the building should be, what category the building should, and this is more aligned with international code. So which is great thing that the code has now getting more and more aligned towards international codes. And then we did some comparison study that, how much is the percentage, the comparison between the zone factor multiplied by importance factor for a given typology of the building. And then we could see that it's not significantly. So 2016, if I say importance category 1, 1.2, 1.5, 1.9, 2025, all importance categories are 1, but the return periods are different, right? So with the different return periods, ZI of 2016 and Z of 2025. So if you start looking at those yellow and white numbers, they are not million miles away. They are more or less there, right? Not some locations they have increased, yes, but not significantly. So it's good that the code has now aligned itself towards international and it can be then refined as things progress. So, hats off to the code writers that they have now. Okay, it's complex code to understand, but it is now aligned with maybe ASC7, Eurocode, and whatnot. As a structure engineer, what we should be careful about? Okay, loads is one aspect. The configuration of building, that's is most critical. That you should not have, or you try to avoid. Not, I don't think you should not have, cannot happen for structure engineering. Things are dependent on plot, depending on architectural vision, client requirement. There are few things will happen on our projects. So what we try to do as structure engineers, try to mitigate this, try to get away from these problems, try to explain the architect, try to explain the client that these things are not good for you, or these things are create problem for you. Sometimes unavoidable, sometimes a conversation can help to avoid problems. So irregularities in buildings, whether it is plan irregularity or section irregularity or elevation irregularity, try to avoid them as much as you can. Although code says you should carry out certain tests or certain analysis, code doesn't allow certain irregularities. But then, the plot or the client vision or the project configuration may not enable you to have, or may not enable you to eradicate all these irregularities. There will be some irregularities which we have to work with. The response reduction factors, there is another thing. We design for less seismic forces in reality. And then because this R factor that we have, which is a combination of ductility, redundancy, and overstress. So add those three together, you become a good R value. I think sometimes 4, sometimes 5, sometimes 3, depending on the typology of the building. So this response reduction factor allows you to reduce the seismic load. But remember, we are reducing the seismic load not because code says that. What code says is this particular typology of the building is able to withstand that much of a dB or MC level earthquake by cracking and allowing the energy to absorb or energy to dissipate, right? And that's why different typology of the structures have different R value. Now, flat slabs, I think R value is 3 because flat slab structures are not great in absorbing energy. They snap, there's a punching shear issue. So that's why we design the structure for higher load. That's why your R is low. Whereas your beam slab system or shear wall system, you have R4, sometimes R5, which means that you are designing the structure to absorb that energy. Earthquake doesn't know which structure is designed for what sort of seismic, what sort of R value. Earthquake just hits, but it's a behavior of the structure that defines how much load is dissipated by internal cracking and how much load is then transferred to the structure to getting the actual forces onto the structure. And that's why correct assessment of R value is absolutely critical in calculation of seismic forces. Now, that's on the loads on the building. Then structural systems, right? Tall buildings have loads and loads of systems. Structures is one of them. There is an vertical transportation, MEP, fire and life safety, sustainability. So let's just focus ourselves on structural systems. So there are two options. One is gravity load and one is lateral load, right? In the gravity load, you have different systems. You have cast in place concrete, composite decks, precast, different typology of the building, post-tension, bubble deck. If it is a concrete building, you have RCC, post-tension, bubble deck. If you have composite steel structure, you can have composite slabs, deep deck slabs. If it's concrete frame and steel frame buildings, you can have hollow core, half slabs, delta beams. These are precast segment. Not quite famous in Indian context. Some of the projects have been there on precast. Not quite famous. Delta beam I've not seen much. Good solution there in terms of precast buildings. So I just try to add in a little bit. And sometimes some of these are repeat for most of you, so I'll just zip past. M30 to M50 grade concrete, C30 to C50 if you want to go with European or American standard. What is important when you're prescribing this is how less you can pour concrete. You can go bubble deck, you can go post tension, reduce thickness to reduce your embodied carbon. And I'll touch upon and special talk on embodied carbon a little bit. So try to be light, as much light as possible, because remember a 30-story building, a 250 thick slab, and a 30-story building, 225 thick slab, 25 millimeter times 30 is the total reduction on seismic weight. And that is equivalent reduction on the seismic force. So the horizontal elements have to be defined to the, I would probably say to the 5 millimeters sort of a tolerance. If it is 265, go for 265. If it's 275, go for 275. If it's 150, don't go for 160. Or if it's 125, don't go for 150. Right? Make sure that these horizontal elements, which are going to stack up and increase your vertical load, increase your lateral load, are as optimized as possible. And then you can do multiple things there. Post tension concrete is one thing. I mean, I was fortunate enough recently visited JSW's plant in Bellary. They took us to their low relaxation pressed concrete, fabrication, low relaxation pressed concrete. What you call the manufacturing facility. Amazing thing. Fantastic work that they are doing there. Low relaxation helps you to reduce the post tension cables in terms of because they can have more force, sustained force other than relaxation losses. So it's fantastic in that way. Then you can go with obviously deck system, steel composite deck. This was a site I visited back in 2018 in Dubai when the building was under Brookfield Place under construction. So you can only challenge with deck slab and steel beam is obviously you have to do coordination with fire and life safety MEP well in advance, or you got to allow this MEP system to come and fit later on. Another challenge here is if you see these sort of beams projecting downwards, and if it is a shell and core building, obviously the people who are coming in and renting these office buildings, they may not necessarily be happy to see this beam projecting down. Instead of flat stoppy, they will have this. So that means there is a restriction on the installation of their false ceiling, installation of their chandeliers or services. So they tend to, prefer not to go for it. But again, in today's world, it's all open ceiling, right? There's no ceiling per se. People don't go for it. They project all the services. And a nicely done steel structure with this sort of opening, properly routing the services, it looks lovely. In fact, it looks much better than a concrete building, because then you can see that the structure engineering behind it, and people feel the amount of effort the structure engineering has taken into this. But one of the challenges with these sort of structures, especially composite deck, they are so light, they tend to become susceptible for floor vibrations. And that's another challenge, that when you do these type of slender or very thin structures or thin floor plates, you should carry out some sort of a floor vibration analysis. Again, there are codes available for that. We can have a separate session on that, on how to calculate floor vibration. And then obviously 2 hours fire rating, shear stud length, because sometimes shear studs have to be, I think I've covered that somewhere. Yeah, here it is. You can have a deck which is 80 mm. You can have deck which is 60 mm web. So if it's 80 mm web, then your shear stud length will go 80 plus 2 times the diameter of the shear studs, which is say 20 shear strut, so that's about 40, 80 plus 40, 120 shear strut. Where is 60, you can go easily 100 shear strut. So that's the trade-off. But 80 deck can span longer, so you can have less beams. It's a multiple permutation combination. One of the thing for shear studs when we use this type of building is the testing of the studs, bent in, bent out test, making sure that the welding is done properly. This is the fabrication yard we visited recently in Taloja in Mumbai for one of our projects where they were doing some shear stud welding, and we visited and we ensured that the welding is done properly in terms of cleaning of the surface, heating of the surface, making sure that the base steel, and it's not the composite deck per se, it's more of a steel section into an outrigger system. But the fact still remains that the shear stud, although the installation is easy, but it's just that making sure that the weld quality of the shear stud with the base material is correctly done. Then there are deep decks, not that common in India, but pretty common outside, especially in UK. You can have the deck built into the steel beam, so you can still have a flat soffit, right? But I've not seen this much in India. I don't know, maybe some of you might have used it. I've used it in a couple of my projects in the UK long time ago, but I've not seen much in India. But deep decks are good. They can span larger, so you have less beams. They can fit in that. But imagine, important to remember that deep decks require the beams have to be of different flange width. The top flange have to be shorter, bottom flange have to be wider, so that the deck can go from top down. Otherwise, threading of that deck on top of beam becomes a challenge. You can't put deck like inclined and put downward. So it has to be the width of the flange, top flange has to be lesser than the width of bottom flange. Bubble deck is another one, which is especially for post tension and reinforced concrete. I have used it. No, sorry, not I have used it. We tried using it for one of our projects, but eventually we could manage to reduce the slab thickness by post tensioning, and the total weight was not significantly low. This gives you a lot of advantage in reduction in total weight. But then again, you have to depend on what is your flow to flow rate, how much is slab thickness, because these bubbles have their own dimension, right? So effectively, a slab thickness becomes maybe 250, but weight of that slab, equivalent weight of that slab will be around 150. But then 250, can you accommodate that 250 thickness in flow to flow rate and services? That's a question. Otherwise, you go with a post tension concrete. Then there are obviously half slabs and voided slabs and whatnot you have. This hollow core is also commonly used, but I've not seen this much except for one project in Dubai where we were doing some peer review where the hollow core was used on Sheikh Zayed Road. Hollow core was used as it was a steel building. Hollow core was used as a flat slab system, but commonly used for car parks. They can go up to 16 meter span, so you can go with car park load and 16 meters. So Mall of the Emirates was classic example where I have used it for 16 meter. Then another project that we had, the Buro tower that I was mentioning, we were looking for, there's a big opening on a residential building, and the trusses and the rest of the structure was steel on top of it. So these openings were, the client wanted a flat soffit. So we then went with hollow core with steel beam. So it's a combination of hollow core slab with the steel beam. So it's also possible for your floor slab. Again, these are hollow core slabs also reduce your overall weight. They are post tension, so they can span larger. They have hollow voids inside, so the weight is less. So advantage. Again, but the challenge here is hollow core slab come with a certain dimension, erection strategy, and the craneage and whatnot here. That needs to be discussed with the client. Delta beam. This is one of the good things. It's pretty common in European, especially in Nordic countries. I think in Dubai also they have started recently. I've not used myself, but I've been interacting with delta beam manufacturers. They have tried something in India. I don't know how successful they are, but this is one of the good solution in terms of how the beam would go. Something similar to what we did here, but here we didn't use delta beam. Here we used I sections. But delta beam is basically, instead of having I section, you can have this tapered web, two of them, and then you can have this voids in the web, and then you can have the hollow core sitting on it. So effectively, you can then pour concrete and you can then connect it through the webs of the beam, through the beam themselves. If you see at the center here, you can put a reinforcement. Is my cursor? I'm not sure if my cursor visible, but you can put a reinforcement and you can connect across the delta beam. So again, it depends on the typology of the building, delta beam manufacturing, and then stuff like that. Half slab is another one. I have used it for, I think it was one of the project in Jebel a small a small industrial project where I used it as a slab. Again, this is half panel. We can erect it and then pour concrete on top of it. So again, it's not the savings of the weight, but then it saves you formwork, right? It saves you significant amount of time on shuttering. So that's an advantage. Again, it's precast. It depends on how the building looks like. Most critical on tall building is lateral forces system, right? They call it LLRS, but I think I prefer LFRS because the force has a direction rather than load. Load, in my opinion, is more what you call more non-vectorial, right? Whereas force, scalar quantity, force is vector quantity, which has a force. That's why I feel that LFRS is better than LLRS, but eventually it's the same thing. We all know IS code. I think this is 2016, but this revised version has come. I didn't bother to change that, but there's revised 2023 version of IS 16700, which has some changes into this. Some different systems have been introduced, but basically IS 16700 tells us to what height we can use. It has its own slenderness calculation, but traditionally, if you look at the structural systems for LLRS or LFRS, you have frame system, you have shear wall system, then you have core supported like outrigger support systems or belt supporting system, tube structures, brace structures, diagrid structures, and hybrid structures. Now, each of them have different configuration, different typology. This sketch at the right, I taken from one of the books from where WSP have shown it. It tells you how different systems can be utilized. Faisal Khan, again, referring him because he was the guru of tall buildings, right? He had done so many of them in US. Big, the best person of tall buildings, I would say, best structure engineer on tall building, which I could. There are a few others, but this guy's much knowledgeable in those days. So he put together classification of tall building structural systems, and you can see this in many of tall building books. I'm not going to repeat it because it's all there. There are some internal systems, there are some external systems, there are some steel building systems, there are some concrete building systems. They can be combined together, they can be facade dependent, they cannot be facade dependent. So it's a permutation combination. With that, recently people have come up with slightly more advanced version of classification, and they call it interior systems and exterior systems. And interior systems, we have about 8 of them, brace, hinges, and this slide I've taken from the course that we had for tall buildings structural systems. Tall building structural systems. I think there might be some repeat of that, but there are 8 systems for interior, and some of the buildings which are built using those 8 systems are here. One of my building is this one, the Mac Heights, which is about 320 meters. There's another one which I've been working on. This is outrigger. This is that Buro Tower, 4 wall only. Again, one of my building. Not used on any of these buildings. Brookfield Place, which is what I was just saying, steel building. And Burj Khalifa. Burj Khalifa is basically the buttressed wall building, which is kind of this. Even Jeddah Tower is buttressed wall system. And then there are exterior system, which is a die-grid or external truss system. And there are 7 number of them. This is a new classification. So 8 interior systems and 7 exterior systems. And some of these buildings, exterior systems are here. I not put in one of our projects. We are currently working on die-grid, which is this one, this system. We are working on about 200-meter tall dry structure system at the moment. It has its own challenges, exterior system, because facade, structure interface, steelwork mostly, so steelwork connections, floor to die connection, die holding back die fabrication of node, a lot of challenges, right? And then how we select these structural systems. And again, this is a repeat from my session that we had on tall buildings. There's architectural and aesthetic requirement. There's a obviously shape, size, and logistical challenge. You might have a project which is sitting inside a city center where you cannot take long span steel beams and steel trusses. No choice than to go with concrete. Whereas you might have a building where you can take steel, but your cranage is limited. Other areas you might have a challenge on materiality. Couple of projects that we have worked in the south part of India, the client has said don't go anything beyond M50 concrete because that's not readily available, or there's no track record of consistency of getting that strength. Availability is there, but track record is not there. So sometimes you have that challenge, plot shape, logistical challenge. Then I guess again materiality, maintenance. It's another challenge in terms of how 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 the building is going to be maintained. Is it a leased building or is it a sold building? If it is a residential building, obviously we don't want to get into maintenance because that's going to be sold, and it has to be idiot proof because the housing society is forming after that. They may or may not maintain the structure of the building. They might maintain the finishes, they might redo the finish, but the structure may not be maintained. So that's when we as a structure engineer has to advise client that look, what is your end users? What is the meaning of it? Are you going to maintain it? Are you going to lease it? How often you are going to maintain it? Is it going to be given to housing societies eventually? So we can then talk to the client saying that these are the advantages of different systems. Slenderness is another challenge on criteria of selection. Sometimes you have to do certain buildings robust, although the building may not be that tall, but building might be slender. And when I say slender, height to LLRS or LFRS system ratio, or height to width ratio, so to say, is more than 10. Where when building starts becoming 7, more than 15 is very, very challenging. More than 10 is the borderline case. Wind and seismic forces. Our country is huge. Different wind speeds in different parts of India, different seismicity in different parts of India. So one system working in, say, Bengaluru, where wind speed, I say Bangalore is a paradise for structural engineers. Low wind speed, low seismicity. What you want, And ironically, we have not seen that many tall buildings in Bangalore for whatever reason we have, but it's paradise. Low seismicity, low wind compared to Delhi, where you have high seismicity, reasonable wind, compared to Kolkata, where you have medium seismicity, high wind, compared to Mumbai, where you have average 45 meter per second wind, and which is reasonably higher, 44 meter per second, but similar to Dubai, which is 45 meter per second. But then medium seismicity. So it all depends on which seismicity you have. Typology of the floor plate, as I just told you, gravity load system, and these are all selection criteria for structural systems. Sustainability. If the client is going to maintain the building, what are their sustainability drivers? See, material reduction in material is obviously everybody wants to have, because nobody wants to spend more than what is required. So that is going to happen eventually. By default, it's going to happen. That's how our clients look at it. But then, are we using the material efficiently? Is the balance strike right in terms of your grade of concrete, grade of steel, structural steel versus composite column versus normal column, constructability, site challenges? It all depends on that. Loads and cores, obviously, there are international standards, there are Indian standards. We tend to use Indian standards. What I've seen is Indian standards are slightly conservative. I would say slightly, because I think there is reason behind it, because not necessarily every structural engineer in the country or every construction happening in the country is done by a proper structural engineer. So that's probably the reason why code is a bit conservative. A qualified structural engineer may not necessarily be appointed, especially in district places or taluka places, where things might just happen. Last 10 years I've been doing, I'm going to continue with that 10 years, next 10 years. So perhaps that is the reason why codes are a bit more conservative. Occupancy comfort, I talked about it in terms of the feel of acceleration, feel of movement of the building. Uh, Burj Khalifa moves. We all know that, right? Burj Khalifa moves by 1 meter. It sways, right? I was not on a tower, but I was part of the Burj Khalifa team when I was in Middle East. I was not on tower, but I was sitting next to the building and we were looking for other buildings around the tower. But obviously, when you are sitting in the same office, you can understand, right? You can discuss, you can talk. It moves 1 meter, but do people feel it? No, because there's nothing in front of them which shows them that it's moving. But the moment it jerks, then people feel unsafe. That's why that acceleration and jerk are critical than the actual movement of the building. Soil condition is another one which defines some of the tall building in terms of your foundation, whether it is cellular raft or the normal raft or pile foundation or individual footing and stick slab. So many options, right? Uh, Materiality, I said this about material selection. Construction schedule and complexity. Again, typology, efficiency of construction, which is more to do with how soon the material can come to the site. We are doing a tower in middle of nearby Mahalakshmi racecourse, and the getting the concrete on site has always been a logistical challenge. So we had to work with the contractor and with the PMC team as to how the foundations can be constructed for this tower in terms of vertically slicing and horizontally slicing the footings foundations. So again, it depends on construction schedule, complexity, reach of the material, and some special topics on tall building, which are kind of specific to tall building, not necessarily every building. One of that is dampers. I have used dampers on spires, not on the buildings. Now, dampers are done for multiple reasons. Uh, Perception acceleration and reduce that, wind-induced fatigue, wind and seismic force reduction, fluttering effect reduction. There are so many things for dampers. And there are different typology of dampers. The one I use as the simplest of that, which is the hanging chain damper on a couple of my spire projects in Dubai. We could see that when these type of hanging chains are being put in, the vibration and the fatigue just drops down, right? But then these are very tiny dampers that I had used. But then if you see Type A 101, huge mass damper, right? On top there, hanging chain mass damper. Then there are different typologies of water sloshing. One of the damper that we were looking for, that the Mac Heights project in Dubai, eventually we didn't require that, but beginning of that building was 400 meter, 400, I think 420 meter, then reduced down to 330 meter. So 420 meter required damper, and we were looking for option of going for hydraulic dampers like the water sloshing or water column dampers. Then there are a few others which are hydraulic piston. Hummingbird is another damping agency. And then there are a few others who prepare, who come up with their own proprietary dampers who can put in on your floors. You can put in the top. They come and they discuss as where you can provide these dampers. There's a good publication from CBU, Damping Technology in Tall Building. I think it's perhaps not available at the moment, it's out of print, but it's a very good book to understand damping in tall buildings. Differential shortening is another special topic in tall building. And when I say differential shortening, stresses in core wall and stresses of column, those are the two drivers. And then most critically, this is most critical for open plan offices where you have perimeter columns and core wall. So the stress in the core wall is relatively lesser compared to the stress in the column. And we all know PL over AE, that's a deformation. So PL over AE of the core wall becomes less compared to PL over AE of the column, and which then creates differential shortening or the column shortening more compared to the core wall, creating this sort of a situation in the slabs. So we have to calculate, and in a normal building, 10-story building, you perhaps don't need this, but when you go for 30-story, 40-story building, you definitely need this pre-cambering calculation, column elevation, they call it. So you calculate this short term and long term, and then you find out, okay, how much you can correct it. There's methodology available to do this. and for short term and long term both. And then how you correct it? Basically, you which is called a super elevation of column. So suppose you have every floor, the first floor settles by 5 millimeters, second floor settles by 5 millimeters, third floor settles by 5 millimeters, say like that, right? So effectively, fifth floor you'll have 25 millimeter settlement. Now 25 millimeter settlement when the fifth floor is cast, right? When the floor above are cast, the fifth floor will settle further, right? So there's going to be that lot of interrelated and construction sequence related calculation. And then when you do this calculation, then you have to say, okay, I'm not going to correct the column at every floor because that's just not possible because shuttering. But I'm going to correct column by, say, at a lower level, every third floor, maybe every fifth floor. As you go up, the column shuttering effect reduces, then you correct them at every 10th floor or something like that, right? Uh, Controlling factors, again, column wall sizes, concrete strength, different concrete have different E values. When you do this, we highly, I would highly recommend to carry out your E value test. We do that for all our tall buildings. Reinforcement percentage, because your composite section becomes a E value of composite section rather than just concrete. Again, slab weight, lighter the better. So keep that in mind. Uh, Humidity does play a role in creep and shrinkage, so that's another challenge. Temperature of casting, ambient temperature variance, that's another challenge. So there's a lot of factors into this. And then this, again, this is more specific to tall buildings because differential shortening is, normal building you perhaps is not that critical. Construction sequence analysis is another one for tall building specific because you will have transfer beams or transfer structures where load will be accumulated as things progress. Your ETABS analysis will not give you ETABS analysis. There's a hand of God which is holding the entire building until you construct it, until you run it, and then the hand of God releases the building and the building will settle. In reality, your building will all the transfer beams will see load in incremental manner, and that's why construction sequence is critical. And when we do construction sequence, again, it is a long-term and short-term both calculation. Then people have now gone to performance, not now, perhaps 20 odd years now, performance-based design for seismic design, PBSD. We have used it in and at least two projects I've used on PBSD. But then there is people are also going for PBWD, performance-based wind design, which I have not used personally, but I've seen MKA from US. They have done a couple of projects with performance-based seismic design. My good friend used to work in Atkins previously, now is working there. So get a feed from him in terms of what's happening on that. Floor vibration, I talked about it in terms of footfall analysis and especially on the long span lighter structures. These are critical. That when you're even in an office building, you're sitting there and somebody walks in a corridor and you start feeling the vibration. That's not good. So that's where we start calculating this footfall vibration, floor vibration analysis. A separate topic and topic on its own. Then we did comparative studies for steel and composite, different typology, different what you call headings where these buildings perform better, and some building in some heading they perform better, some building some heading they don't perform. So again, this is something that you need to discuss with client, architect. Obviously, client, if you are going to a residential building, no choice, and you have to go with concrete anyway. But if you're going for commercial buildings, we are going for 300-meter tall or 250-meter tall commercial building, then all these things will matter. Fire protection on steel buildings, another one. We all know that steel loses about 50% of its strength when the temperature hits about 500 degrees centigrade. So it's not that the temperature is going to go to 500 degrees, but it's just that we have to make sure that the building is stable, integrated, and then insulated under fire. And normally, NFPA floor plates have to be designed for 2 hours fire rating, and verticals have to be designed for 3 hours fire rating. Now, normally we don't do that in India. We do everything 2 hours. But imagine a 40-story building catching up a fire. Not that the fire will last for 3 hours, which is another dimension to that. That what are the consumables? Is the fire going to be it will consume the furniture, it will consume perhaps carpets, it will consume the HVAC ducts and whatnot. But once it comes to concrete, it will not consume anything. So what are the consumables that fire can continue with that intensity for 3 hours? That's a question, right? And that's how we should look at whether it is 3 hours fire rating or 2 hours fire rating. And then this guidance from IS 100 tells us that period of structural adequacy, PSA they call it, should be greater than fire resistance level defined in code 16412. So effectively what it says is structure has to be adequate for more longer period compared to the period required for evacuation and extinguishing of fire. So 2 hours seems to be a reasonable thing, but sometime in tall buildings like 300-meter, 400, 350-meter, 250-meter tall building, you might want to consider going for higher, especially for vertical elements. There are different fire protection strategies and different materials available: intumescent, fireboarding, vermiculite, multiples of them, and you can discuss pros and cons of with the manufacturers. Probably not do that. Corrosion protection for steel buildings, another challenge, especially exposed steel. If it is built into concrete, no problem. If it is fire protected, no problem. But if it is not fire protected but external, then corrosion protection is a challenge. The biggest challenge with corrosion protection, or even for that matter, intumescent fire protection, is the period of warranty. The structural design life is 50 years, but these coatings, they will not have 50 years design life. They will maximum have 20 years or 25 years. What happens post that? Because these products are used with SA 2.5 surface finish. In a live structure, you cannot achieve. How are you going to achieve SA 2.5 in live structure? So that becomes a challenge. So when you are discussing on a fireproofing, I think, or corrosion protection, ask question that what happens after the design life? Is that going to be repainted on the partially painted or sand paper finished steel product, or does it require that SA 2.5? And if it is required SA 2.5, no use then. I mean, you cannot achieve that on site. So that's the thing which you should be careful about. And then construction speed is another challenge in tall buildings, because the faster you construct, the faster the revenue will start for the client. And then how we can do that? Obviously, there are multiple things that we should be careful about. Repetition of floor plates, uniform floor to floor height, so that you can repeat the formwork. Slab thicknesses, uniform beam sizes. Avoid transfers. That's a big one, right? Not necessarily every project can afford that. Sometimes the residential project with my one will definitely have some transfers. So try to optimize the number of transfers, work with architect, work with client, reduce number of grades of concrete. That's another thing, that multiple grades will create multiple problem on site. PFCs rather than, use steel work and parallel flange steel sections rather than tapered steel sections, like ISMBs and ISMs. Instead of that, use UBs and UCs. Waterproofing system, make sure that you have done properly in terms of integrated or external waterproofing system. Sometimes shoring the temporary retention system becomes a dead investment into the project. So try to utilize that in your base structure. We have done that for one of our projects. Again, but it has to be designed for 50 years, not 5 years. Normally, temporary structures are designed for 5 years, and then you are expected to take it to permanent condition. But then when you discuss with client, these are pros and cons that you have to tell them. And then there are other terminologies in construction, precast stairs and top down. Top down, yes or no. Modularity, aluminum shuttering that we discussed, slip form of core. Bit on embodied carbon, again, one of my favorite topic. We all know that the temperatures are going up. There's a lot of emphasis on reduction in carbon. A lot of work has been done in air conditioning system, your diesel generator system, but not much is done on embodied carbon. The total carbon of the building is embodied and operational carbon. There's a lot of work done in operational carbon, but not on embodied carbon. So one of the things that we should be mindful about is the more the material we put in, the more the embodied carbon. So obviously we are, by default, we don't do that because client pushes to reduce the material consumption, which is great. But at the same time, do we require particular grade of concrete? Do we require 28-day strength? Imagine, you have a M50 grade concrete, right? And 28-day strength, you require a cement of maybe 350, 400 kg per cubic meter. Are you going to load that much of a load on that particular element at 28 day? You are not, right? Because building is going to be constructed in next 6 months or maybe next year. So do we really require 28-day strength? Maybe we can consider 56 or even 90-day strength. So that's a question to be asked, that do we require? So you can drop down the cement content, which means you can drop down the embodied carbon. Cement is the biggest culprit on embodied carbon. So, there's a lot of work has been done on operational carbon. Embodied carbon hasn't been done. So we have to, as structural engineers, obviously there's going to be a challenge from the client side because they want to increase the speed of construction. So that's there. They want to strike off the formwork for the beams and slabs quickly. That's a challenge. But at the same time, we also have to think about the earth, Mother Earth itself. What are we going to do? And it's our responsibility. Structure is our responsibility that we are creating this, right? So discuss this with architect, discuss this with client. It's not one-stop solution. Everything cannot be possible everywhere, but there are things which discussion can help. There are some statistics here in terms of what we are responsible for. About 60 to 70% of embodied carbon is where we are responsible. And when I say 60 to 70% embodied carbon, in a building, all the things which are constructed will have a carbon. 60% of that or 70% of that is driven by structural engineer. So imagine the impact, each building, so many buildings, right? So obviously we should be thinking about what are we going to do? And then there are obviously methods available to measure this embodied carbon in terms of at the design stage, at the construction stage. There's BSEN 15978, how to do this. ISTruct UK has given its calculator as to how to do this. The routes of reduction, and I can have a separate topic on this, on embodied carbon. So ISTruct has this how to calculate embodied carbon. That's good one. Then there's embodied carbon calculation for IC. That's a good one. Material factors for India. That is 2017. That definitely requires some update now. A lot of EPDs. What do you call it? EPD product declarations, right? The product declarations basically says that a particular product has X amount of embodied carbon built into it. So more the EPDs available on a project, more will be refined your analysis. But most critical to remember that it's not the value that you're looking at, it's how you're trying to reduce the value that is more critical. The value can be 1,000, but it's in the beginning of the design at the concept stage. But that 1,000, can it be reduced to 500? I mean, I'm just giving some numbers. It can't be 1,000, but maybe I would say about 800 or something, and then it can be reduced to 500 kg of embodied carbon per kg of per square meter of concrete, per square meter of construction. Some of the challenges that we have is obviously domain knowledge into this, sustainability in terms of understanding of this, digital technologies. Some of the projects we are working on, most of our projects are on BIM 360. So it becomes easy for coordination. It becomes easy for record keeping. LOD 200, LOD 300, sometimes LOD 350. Accountability of ownership. Make sure that accept the mistakes. I mean, there is nothing harm accepting mistake. There is no point debating on things which are non-debatable. Communication is absolutely critical. That's one of the things which I've seen us as Indian engineers, we lack. We lack in communication, clear communication in written English, right? And why English is because that's a language of communication. That's the language we learned about engineering, right? We can communicate in local language, no problem there. But and then when I say communication, it's not just letter writing. It's a sketch is also communication. A clear sketch is so critical to understand. They say pictures talk, what 1,000 words or something like that. Right? A good sketch is good enough rather than writing a long essay, right? So that's on a communication. And some of the projects that I worked on so far, the MACIs, as I said, 330-meter buttress core wall, Ubora concrete core and frame, with the hotel, which is recently, before this was 2019, I think it's finished now. 225-meter concrete core and outrigger, Bay Gate Tower in concrete core and outrigger, Shine Tower in Abu Dhabi, outrigger, then some concrete cores. Most of them are concrete core and outrigger. This Tripoli tower on the right never happened because there were twin towers, but then eventually there was unrest and the project, we were working for a contractor. We did piles and then unrest happened and everybody had to come out of the country. Sharjah Tower, Saraya, these are all UAE and Middle East projects. I have some Indian projects here also. These are all UAE. Here we go. Some of the Indian projects that Prestige, this is what I was saying, 315-meter. It's going to be India's 315 or plus minus. I don't know, remember. I think 300 plus, let's say. India's tallest commercial. Then Section, there's another one. MH99 under construction. Then Raghava, we are putting 175-meter core wall with shear walls and a bridge on top of it. Aranya, 290 meters. 180-meter GHR. Then this Amravati that I was talking to you, die-grid structures, 200 to 225-meter tall buildings. Again, concrete core wall and steel die-grid. So at the end, what I can say on structural engineering is it's basically giving safety to public, right? And with what? With only approximate assessment of our materials and loads. Analysis with tools which are again approximate, right? Withstanding forces which are probabilistic, right? See, so many unknowns there, right? But we as structural engineers, we say that, yes, here is my certificate of stability. And it's a big thing. We are giving the confidence to the developer, confidence to the architect, confidence to the people living into those buildings and families, moms and dads living into that, saying that you are in safe hand, right? That's our responsibility as a structural engineer. So when we design it, keep this in mind that we're not designing for the sake of designing. We are creating spaces for people to live, people to travel, people to communicate and whatnot. So once we think in those lines, obviously our responsibility goes up. And okay, pay scale may not go up. I'm not saying pay scale will go up. You have to be passionate to be a structural engineer. I keep telling to all my grad engineers saying that you have spent 4 years of civil engineering and 2 years of master's degree. You better be passionate about structural engineering, otherwise no use, right? So passion has to be there, but at the same time, make sure that we are, taking the responsibility. Those who have listened to Ashraf Habibullah, ETAB's boss, right? He talks about it quite a lot on structural engineering. An amazing person, right? So that's about it for me for today. Feel free to ask questions.
Excellent presentation. Because so many questions, I will tell Vikas that please 3-4 questions only, and then others can be they can write the question and then you'll answer later on.
Yeah.
Vikas?
Yes, sir. Yes, sir. There are a few questions in the Q&A. First question is Mr. Raghava Gopal Setti. In wind tunnel testing of a tall building, the structure in the neighborhood are also placed adjacent to the tall building while testing. Up to what distance is this neighborhood considered?
Okay, very good question. They call it disk, which is about half a kilometer. Anything beyond half a kilometer, it's not going to, the impact of the neighborhood will not be felt by your project. So half a kilometer, 500 meters. Can I take next one? Vikas?
Yes, sir. Yes, sir.
Yeah.
The next question is
Very easy.
Raghava again asked, while discussing POE, you mentioned 1% POE for special buildings. Instead of 1% POE, why we cannot as well have zero POE?
Probability of exceedance. You can have
Yeah.
probability of exceedance, 0% probability of exceedance, but then what force you are going to design it to? It's a massive, massive force, right? Again, as I said, it's a probabilistic analysis. That's why the code is
Yes.
going to that, right? 1% probability of exceedance is probably the maximum one can consider. 0%, A, you will have a problem in calculation of return period. B, you will not be able to justify that sort of force coming to the building and impact of that on the construction and the materiality and what, right? So you can consider, technically you can, but there's no point. It's like I've wore my belt. Do I have to wear my braces? Right? It's a belt and brace, right? So do I need to be extra careful? I mean, if client willing to pay that much, why not? Go for it. But it's not required.
Yes, sir. So next question is, what are the advantages of using delta beams?
Very good. Delta beam, see, you can go to the website, you can talk to them, and then they can tell you more advantage and disadvantage. But the biggest challenge, biggest advantage that I see is a flat soffit. You're still going for a steel building, but your beams are not projecting below your soffit, right? Which means when you are opening the door for a potential tenant, the tenant is not going to see these beams coming down at every interval and then thinking, how am I going to do my services into this? Because normally your office building, normally this is going to be used for office buildings, they're long span steel structures. So when you are going to office building, traditionally or normally, not even traditionally, normally you will do shell and core, and the tenant will do fit out for services within their tenant space. So the tenant would definitely want, whoever is renting that apartment, that office space, definitely want a flat soffit so that installation of services becomes easy, right? So a flat soffit is one big advantage. Second advantage with delta beam is it is because of the shape of it doesn't rotate. Like the one which we did on you brought our receipt, we had an I section, but I section has a very less lateral torsional buckling capacity. So we had to lower them properly on both sides at the same time. Whereas delta beam, because of the shape of it, it doesn't rotate. So you can load on one side, it still stands the shape it is in its own shape before you start loading into other span. So construction, it becomes easy. And obviously fireproofing and whatnot, yeah.
Yes, sir. Sir, Mr. Dipankar Mukherjee asks, I am MTech student in structural engineering. Please guide me related to MTech project in tall building.
It all depends which university you want to go for it. I mean, go to NITs and IITs because they are at the forefront of various development happening in India, especially the code and material testing. But one of the things perhaps you should consider if you are going for again, what is your aspiration? You want to become a practicing structural engineer, or you want to become a professor? Go for masters and go for PhD and become a professor. Again, it depends on that. Um, Tall building, there's so many topics, man. I mean, creep shrinkage, E-value, composite construction, fireproofing, fire assessment of multiples of composite columns. So many topics.
Thank you, sir. Mr. Fahad Ali Khan asks, while deciding the LLRS of tall buildings, we release some of the beams who are expected to observe lateral loads to achieve the behavior as per the code limits. Is this method of releasing the beam is practically correct since the same beam is going to be cast monolithic at site?
Very this is a peculiar question for every residential tall building, especially my one shuttering. Yeah, you are correct. You cannot practically have that hinge in a detailing. I mean, you can, but very difficult to execute that on site. But when you are saying this hinge, what are you trying to say is there's going to be cracking in that beam at the time when the earthquake hits. And as a result of that cracking, the beam is going to rotate, and as a result of that, it is going to have a hinge. That's the philosophy behind it. Now, whether the beam is going to crack, or it will not crack, or it will partially crack, it all depends on how your depth of the beam is, where it is connected to the wall, whether it is out of plane or in plane, all that stuff. But yes, you are correct that we are not detailing it to have a hinge formation. You can, but normally people don't detail it that way. People just take the reinforcement. But one of the things that's what you can look at is reduce the moment carrying capacity of the beam, because you don't need that when you're designing it. You don't need that anyway, because you're designing at the hinge, right? So there's no moment at the support. So then the reinforcement going to support, make sure that you have only that much as a minimum reinforcement required in the beam as per the code requirement. Don't take all the top bars or all the bottom bars into the support. So as a result of that, you are creating a weak section in the beam, which is kind of mimicking your analysis.
Thank you, sir. This is the last question by Mr. Manik Bhushal. Operational carbon and embodied carbon are very interrelated terms. Embodied carbon finds reference in ICE manuscripts to cite for material related aspects. But where does operational carbon finds references?
Look, I'm not an expert of operational carbon, I must say, because operational carbon is more to do with MEP systems, operations of building like glass, air conditioning, maybe your temperature control, humidity control. So you probably have to refer to somebody who is into that, like a mechanical engineer who's doing tall buildings. But operational carbon, I'm not sure whether operational and embodied carbon are interlinked. Embodied carbon is the carbon which is already built into the building before even building starts operational, right? So the concrete, the material that you're using for ducts, the facade system, the reinforcement, the foundation, all that is already built before even building start operational. That is embodied carbon. And then embodied carbon gets added in lifespan of building when you refurbish the building, when you retrofit the building, or when you repair the building. Even that time also embodied carbon gets added, modified, or whatever. On the other side, operational carbon starts when the building becomes operational, like your lifts are starting, then it's consuming energy. Your air conditioning is starting, then it's consuming energy. Your lighting is starting when it's consuming energy. So that is more to do with operational carbon, day in, day out. And there's a lot of emphasis given on operational carbon, as I said in one of the slides. A lot of emphasis has been given on operational carbon in the last 20 odd years. And if you see the efficiencies are built into the air conditioning system, the electricity system, the facade systems, amazing level of expertise have been gone in there. Whereas embodied, not much. And that's why I think it's our structural engineer duty to highlight this to the client, to the architect. Some of the architects know it anyway. Most of them would know it. Clients, some of them would, some of them don't. I've seen clients who are managing and maintaining their commercial properties. They are more into this because they generally tend to get finance from FDIs, foreign direct investments, and people who are financing them definitely ask question about this embodied carbon. Whereas developers who are into only residential market, again, why would they bother, right? So unless there is and this is something which one of our conversations I had on embodied carbon, that there has to be, if the developer is taking that pain, whether it is delay in construction because of low cement content, or maybe sourcing certain material, maybe construction cost has gone up or whatever, that developer, because the developer is having aspiration to become a low energy building, even if it is residential, that developer should be benefited by maybe FSI. It's, easy solution, right? We call it transport TOD development. Like, here we go, embodied carbon drop down from here to here, get certain percentage FSI to client or developer. So that will give them a benefit or reason to go for it. Otherwise, we all will be talking about, especially on residential projects. Commercial projects, I think there is no choice. But yeah, I mean, I'm not the right person to answer your operational carbon question. Sorry.
Thank you, sir. We have some more questions, but I will forward it to Ms.
I
Rui
mean,
Yeah,
because,
yeah.
I mean, excellent presentation, Abhijeet.
Thank you.
I have questions. Can you give me 2-3 minutes
Yes, sir.
before we conclude? See, the utility part, I mean, our plumbing system, EMP, I mean, there's so many things that will come in the building. See, I mean, how structural engineer can coordinate with the other person, because we have to decide everything right in the initial stage, so that there will
Yes.
not be I mean, dismantling later on. So this is my first thing. Then now the climate change and global warming. How we can think of making the structure uh, resilient.
Yeah.
Then the third thing is now this instrumentation, structural monitoring.
Yeah.
Uh, what are the things that you have I mean, doing in the tall building structure? Then finally, the how we can reduce the carbon footprint. I mean, these are the few things. Just think over, and then if you can spend 5 minutes more,
Yeah,
I'll
sure,
be glad.
sure. Reduction.
Please continue. Please
Okay,
continue.
so yeah, so utility coordination is absolutely critical. Buildings is, you know, skeleton of concrete is not a building, right? It has to be livable thing. That's why buildings are built. People have to live into it, right? Structure engineering, take this postulation that structure engineers are bones of the, maybe one of the slides that I've given to another presentation, I've done that correlation.
Mm.
Bones in body, right? MEP are veins and all the things that take muscle and all the take muscle is structure engineering, bones and muscle is structure engineering. All veins are basically taking all the blood up and down, right? Then comes the skin of the building, which is architecture. Then comes your dressing, which is your interior design, which is your exterior design, all that stuff. So just a skeleton of concrete is not livable. So utilities coordination is absolutely must. So normally, it so happens that we have to work as a structure, we have to work with architect and MEP consultant and facade consultant. These are the three critical disciplines that we have to work. So when we start, bidding for any project, we ask these questions to our clients: that who are these people? Are they are they involved into the project? Are they embedded? Are we going to start? Okay, they may not be embedded or they may not be involved, but are we going to start together? Or are we going to start that structure will start 6 months ahead of MEP and suddenly MEP comes in and says, I need duct here and cut out here and cut out here. No, that doesn't work. So that has to go hand in hand, the coordination between MEP. And normally for tall building MEP consultants, there are many of them. We have our own MEP wing also for who does the tall building for us. So, but then there are a lot of other MEP only consultants who have tall building experience. Then they know what it takes for structure engineers. Because by experience they will tell you that okay, here is my duct taking my fire pipe. Here is my duct for plumbing. Here is my shaft for electrical conduits. Here is my shaft for vertical, chill water up and down. Here is my fire tank connection pipeline, gas pipeline. There's so many of them. There are, if I remember it, there are about when we tender out MEP system, there are about 13 different packages of MEP,
Mm-hmm.
IP, AV. There are so many of them, and this every item has to be will have impact on structure. And this is I'm talking about just commercial, residential. Commercial central air condition is one level up. You go to
Mm-hmm.
hospitals, 3 levels up, because hospital will have a lot of other services, hospital related services, medical services, which have to be
Right.
coordinated with structure. So uh, yes, you are correct that it is structure engineering cannot be done on its own, right? We are not buildings, especially perhaps bridges, maybe architect and structure can go hand in hand, but buildings, it is a living place, people are living there, so you
Mm.
have to be livable. So just a concrete
Right.
skeleton is got it good enough. Coming to your climate change and impact of that on
Mm-hmm.
a structure, yes, temperature increase in temperature has an increase in humidity, has a different challenges in a different part of the country, or for that matter, different part of the world. Uh, One of the things that we have seen climate resilience is water tables and groundwater levels. That is critical to understand that what is going to happen in next 20 years, where the groundwater will be, whether it's going to go down, going to go up. Like city like Mumbai, where your sea levels are going to rise, groundwater table is going to rise. Whereas city like Delhi, or for that matter, city like say inside inside the country, away from the seashore, we are doing a lot of groundwater pumping. Your groundwater is going to go down. So these behaviors will change. The humidity is going to change, and that will have knock-on effect on long-term concrete behavior, humidity especially the exposed concrete surfaces. Enclosed concrete surfaces, nothing changes, right? So we tend to consider a variance of 2 degrees and humidity 5% humidity change, and that's how we assess it. SHM, so, structural health monitoring. It's a topic in its own. On the Mac Heights project, we had multiple rounds of conversation with the client because of the shape of the. There's another project where we did this structural health monitoring. So you have strain gauges, you have pressure cells, multiple. These two come to my mind now, but there are a few others where you can utilize them and get a data. You can have maturity meters also. These days they are using maturity meters to assess the actual strength of the concrete, at what date a particular strength can be achieved in a concrete. So maturity meters helps you there. A lot of development has happened on SHM, and then there are specialists on SHM only, structural health monitoring only. And then they tell you that corrosion rate, they tell you when you're doing protection, like corrosion protection you are doing, then what is the rate at which the corrosion protection is losing its ability. Then there is I've done, not on building structures, but I've done a couple of wharf structures in Chennai. We did this cathodic protection. So that's another thing, active cathodic protection. And then your last question is carbon footprint reduction.
Yes, right.
Right. So carbon footprint reduction, see, one, obviously, from structure engineer's perspective, keep everything, just sink in one level down, and taking the chaos out. We have two materials, steel and concrete, majority of them, right? There's a wood, there is timber and glass and whatnot, but I would say 95% of the 99% of structures in India are concrete and steel. Now, how we can optimize this? We are optimizing it for client anyway, because our clients are very demanding in terms of material consumption. So by default, we are doing embodied carbon, reduction in carbon anyway. But what is also important for us is, as a structure engineer, is are we doing it correctly, right? That, for the sake of argument, say transfer beams, right? Now, are we designing the transfer beams correctly? What happens generally, and this is human tendency, that if you are not confident, you put an extra steel. If you're not confident, you put in maybe extra half of 5 centimeter of, or maybe 10 centimeter of concrete. It's not going to change embodied carbon significantly, but that's a mindset, right? You add that on various projects, you have a challenge. Then this is one side of it. The other side of it is over specifying, right? Sometimes what happens is, okay, people know that embodied carbon is there, cement content is lesser the better, so they drop down the cement content, they use GGBS or silica fume or PFA or whatever. But then you are using that for most of that data, or most of the material, for maybe 10 projects, and remaining 50 projects you're not using it because that material may not be available for those 50 projects. So effectively you are not saving the world, you are just saving that particular project. So that use of material has to be done very judiciously, that how much I'm going to use it, and is it worth using that much, because the material itself will be expensive, the travel costs and the embodied carbon in travel will be high. So that's a question. And the third thing, which is the most critical, is questioning on the loads, right? The loads is the only thing that a structure engineer can, have a say into it. Right. Question it on seismic load, question on wind load, try to optimize it, question on vertical load. As I showed you that one of the slide where lie load, right? Try to work with architect, try to work with client and understand what their intentions are. I have another set of slides on embodied carbon and how to reduce it, but these are the things where you can say, how we can reduce for new form. For country like UK and US and Western world, first question starts, London, I've asked my colleagues in London that how you manage it. The first question in planning permission is why you want to build it. It starts from there. Do you need to build? Then can you use the existing? Because if you see in London, there's a lot of existing facade being retained and building have been refurbished. They don't want to change facade because it acts on a, obviously the cityscape they don't want to change, but also it saves on embodied carbon. So do you want to build it? It starts from there. Whereas in India, I don't think we can afford that because we are still a developing country. So do you want to build is not a solution for us, but build smart is a solution for us.
Thank you, Abhijeet. Excellent presentation.
Thank
On
you.
behalf of Indian Structural Engineers and on my personal behalf, I thank you so much for sparing valuable time and sharing your long experience. And I'm sure persons who have listened will be definitely getting benefit out of that. Thank you so much. And with this,
My
let
pleasure.
us now conclude the session.
Yeah, my pleasure. Thank you very much for giving me opportunity.
Let's conclude the session now.
Thank you, sir. Thank you.